Hello everyone, this is Dilleswara Rao from Aeronautical department. From the last few classes, we are discussing on automatic control of aircraft subjects only. So today we will discuss on glide slope coupler and automatic flare control of an aircraft control surfaces by using that root locus plots and what are the control surface inputs and how that integrator functions are being designed for this glide sloping elements. So glide sloping means like you can see in general the glide sloping will be like what it is a whenever there is no control surfaces are in a trim condition. When control surfaces are in trim condition, so you can see how that like you can see how that aircraft will be moving on that air surface without any control surface without any control surface moment, like pitching moment is zero, or yawing and rolling moments also zero. Just it is like a cruise condition only. Like but in cruise condition, it may be in a descent way. Like it's not like a straight way; it is like coming like a descent way only. Like gliding means what glider will how glider will move, like it will be moving like this without any control surface inputs. So for that way, how to design, what are the autopilot system we need to install for getting that auto gliding system, and how to control that gliding system also we will see now. So the ultimate goal for both military and commercial aircraft for all weather condition to achieve a big aviation, to achieve a good aviation experience. Like experience means that smooth operation of that aircraft need to be essential here. So to achieve this goal, it must be possible to land the aircraft without virtual reference of that runway. Like without virtual reference means what? If we don't know where that landway is, that landing runway is exactly placed also, but even though the aircraft should be land with precise condition. So for this can be accomplished by automatic landing system, which will be guide the aircraft down to a predetermined glide slope, and then that pre-selected altitude reduce the rate of descent and cause the aircraft to flare out to touchdown with acceptably low rate descent. So like here when it is getting touchdown and it is running on the runway, so that predefined glide slope and then that pre-selected altitude reduce the rate of descent. Like if we select that predefined glide, like it is approaching that glide, but that gliding angle is that much. So if we follow that glide angle, so that it will be automatically get that gliding path, and automatically it will touch with without any further deviation in flowing. So the longitudinal control portion of that such an aircraft flight path angle, that is gamma. So here it is gamma only. So the altitude, the automatic control of flight path angle without simultaneous control of airspeed, either manual or automatic, is impossible. So this will be illustrated by studying the response of that attitude control system without velocity control. So that will later be coupled with glide slope. So for this analysis, jet transport in the landing configuration will be used. So the appropriate functions by using that longitudinal equations are These are the equations. If you remember that longitudinal equation of motion of for aircraft, if you see, so these are the equations that first the three equations we have shown here. So here the CXT also defined in terms of dou T by dou delta per RPM. So here you see one block diagram for jet transport landing autopilot system have been given here. So here it is showing that the basic autopilot analysis, the root locus for this inner loop has been shown in the next figure. This is the root locus plot for that autopilot system. So here the root locus, if you see that root locus plot, the rate gyro sensitivity was selected so complex poles would lie on the branches approaching to 90 degrees asymptotics. That poles are at 90 degrees asymptotics, like this is the almost 90 degrees asymptotic line has been constructed here. So that damping ratio, here the damping ratio is almost greater than 0.7 only. So in the for this case it will be around 0.866. So for a higher damping ratio will be attaining, because of that outer loop tends to decrease the damping of that complex roots. So for a closed loop poles, that has been indicating in that autopilot, there the SRG will be like SRG means rate gyro values. So rate gyro values, that SRG means rate gyro values. So that rate gyro values are almost 2.5 volt per radian second. So for this, the root locus for the thing have been given here now. So I mean, after selecting the two lobes of the basic autopilot, before autopilot system, the basic autopilot was simulated on analog computer only, and for the aircraft simulation, the complete 3 degrees of freedom longitudinal equations will be used. So that response of that aircraft alone will be like a step elevator input with no velocity control, that has been depicted on the next figure, that is figure 6 you see here. So that has been seen here. These are the frequency response of the transient response of that autopilot system only. You will see that. So it is evident that the great gyro has a little effect on the damping of Fugite mode. So the response of that aircraft includes the basic autopilot for a step theta common. That can be shown in later figure. So here, the necessity of velocity control is now evident, in that the steady state values of gamma is around 0.2 degrees. So here the values results from a positive theta command. So the which will be hoped to will be cause that aircraft to climb positively, like with a positive gamma only it is getting climbing. So however, the nose of the aircraft, if the nose of the aircraft is been rising, then the aircraft start to climb. So at that, the airspeed will be generally decrease. So that will be gives you that increase in angle of attack, that will maintain a required lift also will be attaining with that one. So for the steady state, for a steady state approach, this increase in angle of attack will be greater than that change in theta. And if gamma is theta minus alpha dash, then the result of that aircraft starts at very shallow glide only. So in order for gamma to have that same steady state sign as theta command, so the velocity control command also will be employed for this autopilot system only. So see here, for this autopilot, that root locus of outer loop based autopilot also, outer loop of that autopilot also having that root locus of pole values are been having that asymptotic values only, that is near to that real axis, but it is touching with that imaginary axis. That means that S values are having near to that imaginary axis than the real axis also. If you see that approach of this values also, it is almost near to that real values, but it's not getting touch with that thing. So the root locus is the giving like, the root locus means what? I said like the values of that yes for a particular input, how the values we are getting for different inputs. Like from the amplifier only that suppose the SMP amplifier function values are suppose 0.3, 0.88. Then the if you solve this integrator with Laplace transform function, so the S values will get different values like that. So for that different values only we have drawn these curves. So an automatic velocity control sometimes will be referred as a phugoid damping. So that is that will be that you will show in figure 7. So see here that figure 7 it is that for root locus for that velocity control loop. So this is another velocity control autopilot system also have been given here. So the time constant for the jet engine is suppose 10 seconds, and that may be excessive. So however, if the system can be made operate with this lag, so operate if it is lag, then the performance would be better if that actual engine time constant is less. If you suppose that actual engine time constant for operation is getting less, then only we will get a good values for that autopilot that yes value. So the time represents the required represents the time required for thrust to get from thrust generated from the jet engine to build up that moment build up that moment, so that the U can be changed in air speed. The input to that air block is the change in engine speed from the required straight and level unaccelerated flight. So the first block in the forward loop in figure 7 is a proportional plus integrated network. If you see, one proportional and integrated network is been given here. So this is a throttle servo network, and this is an engine time lag network. So from this only that output is been going to that aircraft control surface. So by adding s equal to 0.1, the velocity and the rate change of velocity are used in feedback path. So both the velocity error and the velocity rate signal can be supplied by a single instrument, that is instrument. So the aircraft transfer function from obtained from that equation, first equation, that longitudinal equation is there now. The transfer function we will get it from that is given here, that is 37.9 cxt into s into s square plus 1.s. This is the transfer function. We will get it from the previous function by adding that previous functions only. So the existing quadratic, the numerator of that equation 2, that almost exactly cancels the short period quadratic in the denominator. It's not a coincidence. So for this reason, if examine that determinant of numerator used to determine the equation 2, that determinant we can make it in matrix form. It will be shown like this. So the result of expanding the foregoing determinant yields, determinant yields types that minor, but the minor of that identical to that denominator for any transfer function will be obtained by using that Fugate mode approximation only. So that Fugate mode approximation, how that frequency response have been given here. This has been shown here for a different theta values and gamma value. How that frequency response has been given here. So see here, this is the transient response of a jet aircraft for a landing configuration at a sea level 250. Here the velocity is 250 feet per second. for an elevator step input, like a step input elevator we have given like this. So, as the short period poles are effectively cancelled by the complex zeros and zeros for that above said transfer function, that is U of S by delta RPM of S. So, the transfer function is the velocity control loop that has no effect on that short period pole. So, this characteristic velocity can be open loop, that can be the simplified transfer function for that open loop will be shown like this. I mean, we can get this equation from previous equation simplification only. So then the transient response of that autopilot for that S amplifier value at 3.88 volt. So for that, if you see here, that alpha, theta, and theta common and the delta values, how that frequency response have been given here. Here the linear changes is there. Here some peak values are there, and here also some linear and peak values are there. But here it is totally constant only. So for that, previously I said no. For throttle, I mean the engine acceleration autopilot system, like for getting the glide, how that throttle servo transfer function will control that throttle, and how that rate gyro values also will be depending on separate transfer function, and that engine time lag, like a time lag means after getting if you are giving the full throttle also, there will be lag on giving that input, the time lag controlling function also been given here. So with this, that if the autopilot system is being designed, and there is a summing amplifier is getting that feedback from that control surface. So for this, that root locus plot is being given here. So here that transfer function of open loop, that closed loop function transfer function is here. So for that, the values are been like from here to here. So here that locus plot is being situated here. So the effectiveness that of velocity control loop that previously you see now TFCL. So that control loop for a damping Fugate mode is very apparent. So the value of product of that CXT delta E can be selected as 0.2 only, but this is we have got it from several experimentation only, like different inputs we have given. For that input, what is the frequency changes also we have seen. So due to that, the damping ratio also been set it to prescribed value. With that, we got this constant value. So the value that has been determined experimentally. So for this value, the complex poles and poles on the vertical branches and have been given in figure 8. So here the damping ratio is 0.182. So here you see that figure 8 before only that figure 8. So the root locus plot only they have given. So the real pole and the real zero is that the dominant route only. The effect of velocity control loop for the basic aircraft with no other feedback is illustrated in the previous after this figure 98 and B. Like that velocity control open loop for basic aircraft autopilot and basic aircraft, like with aircraft with autopilot and aircraft with without basic autopilot also. Here the things have been given here. So there are drastic changes. There is a linear changes in every value, but here there is a drastic gradual increase. After that, there is a constant increase only. I mean the constant value only, because if there is if continuously given that input and if that output also continuously increasing, then this type of linear variation only we will get. But that is not recommended. So if you give that input also at a time, that input it will take, after that that response will be constant only. So this gradual increase, after that that linear that linear changes also, that axial constant changes also, it has been shown here only. So So the as we see that that those the figure that steady state of gamma is not only positive but theta comment also equal to that commented pitch angle only. So it can be noted that the velocity control loop has not affected the initial position of transient response, that is alpha dash and theta, but inertial signs of gamma trace, that gamma trace you see here, that gamma values tracing values. From this the fact is showing that the short period quadratic is cancelled by numerator quadratic, that is in equation 2. So if you see that equation 2, so here from this that numerator is been cancelled, and it can be concluded that velocity control loop does not affect the short period dynamics of that aircraft. Like you can say like from this from this the fact we are concluding that the short period quadratic can be cancelled by that numerator quadratic, like the short period mode, well, when it will be getting that short period mode, will see there will be a lot of damping will be there. But here in the numerator, the values have been cancelled out. So due to that, the velocity control loop does not affect the short period dynamics of that aircraft only. So due to that, we got therefore you can see the velocity control is assumed that either manual or automatic, the short period transfer function can be used for any analysis of any control system employed for control of that flight path angle only. Like here you see, so any of that maybe that is automatic control or maybe manual control, the short period transfer function can be used for that that short period transfer function we have got it from that solution of that longitudinal equation is there now. That function can be used for any analysis of control system that has been employed for the control of that flight. That if you decide, if you want to decide that flight path angle, any of the short period transfer function only we will use to get that glide slope angle, like how that glide slope will be attained by taking that equations from longitudinal thing, and after that after taking that equation also how that things will be going forward also. Here that velocity formulation we have given here. So this is for a part one approach. So there is a part two approach also will be there. So that part two approach will gives you further glide slope based on this velocity formulation, how the glide slope angle is being perfectly designed by using how the autopilot system is perfectly used for getting that glide slope angle also. We will see it on next few class. So in this part one, we are giving that velocity approximation for getting that glide slope confirmation. After getting that velocity confirmation, what are the required output function to function to get that glide slope confirmation also. We will see it on part 2 of this lecture. So this is all about this glide slope coupler a glide slope coupler approximation and the autopilot system designed for glide slope control also we have seen here. So if you have any if you have any doubt and further clarification, you can refer this book, Automatic Control of Aircraft and Missiles by Blacklock. So this is all about this session. So in next session, we will next video we will see that part 2 of this glide slope coupler. Okay, thank you.
Like, share, and subscribe. Hit the bell icon for more updates.